Welcome to this joint EOL RAL seminar, and today we have Melissa Wagner from CU, and she's going to be talking about the duality and connections of UAS technologies and applications in atmospheric sciences. So Melissa comes to us from CU, and where she is the Associate Director of the Integrated Remote and in-situ Sensing Group, IRIS, and leads the scientific activities of the UAS program. Her research combines geography, meteorology, aerospace, as we'll see in her talk. She originally comes from Ohio, where she did a BS in geography at Wright State University, and then took a break for a few years and then came back to do a master's and PhD from Arizona State University. Then she moved on there to the Cooperative Institute for Severe and High Impact Weather Research and Operations, which is associated with the University of Oklahoma and NOAA's NSSL. There she led development of their UAS program and did pioneering work surveying tornado and derecho damage using a UAS, combining that with radar and satellite data and numerical simulations. And lots more besides. So please give a warm welcome to Melissa.
Thank you very much for that introduction. And it's an honor to be here. And in the talk, as my slide and very long title indicates, I'm really going to be speaking to essentially two approaches to UAS and how they're used. So one is in atmospheric sensing, and the other is in UAS land surface characterizations. And so with the UAS land surface characterizations, I'm going to talk and use the Enderlin, North Dakota tornado case as discussing some of that approach. And then really what I'm very interested in is doing kind of an integrated approach to science. And so I'll speak to that as part of the ending here. So for the atmospheric sensing portion, I'm really going to be focusing on our we have a community instrument facility, NSF, called MUSAS, and unpacking that acronym is the Mobile Uncrewed Systems for Atmospheric Science. And so we are really trying to provide a fleet of both fixed wing and multi-rotocopters so we can capture high resolution in situ measurements of looking at the boundary layer. And these have really, we've operated these platforms from a different range of environments. So as the photos show, being in the Arctic in 2020 with the Mosaic field campaign, as well as with the, over in Texas in 2022. And really the nice thing about the SIF, which some people may be familiar in this room, is that we're making this accessible to both researchers and educators, essentially at no cost, through a 3-track request, whether it's education or research-based. And we've flown for about, we being IRIS has, essentially over 1,000 flight hours under the belt and been sponsored by many different funding agencies. And some of the field campaigns that you may be familiar with is Taurus, Atomic, Mosaic, Tracer, Lapse Rate, and Ice Ship, just to name a few. So here's, at a glance, the different types of platforms that we have. We have the Raven and the Super Raven, and those are both our fixed-wing platforms. And the Raven has wind tolerance up to 35 meters per second and has a flight time of about 2.5 hours. And both the Super Raven and the Raven measure pressure, temperature, relative humidity, as well as get 3D wind measurements. The Super Raven is essentially double the size of the Raven. So it has a lower flight time. Really, it says 120, but it's really about 75 minutes here. And then we also have 2 multi-rotocopters. So we have the Helix, and we also have the Copterson. So Copterson does the vertical profiling, and that gets both pressure, temperature, relative humidity, as well as 2D winds. And then the helix is something that can be used, so that's used for kind of specialized sensors that I'll discuss a little bit. Focusing on, and then to kind of get from this slide here, is that both the Raven and the Super Raven have a max altitude of operation up to 5.5 kilometers. Of course, there's kind of asterisks here, being that having to go through regulatory approvals, so FAA and other agency specific, as well as what's kind of cool about both the Raven and Super Raven is that in addition to getting the thermodynamic and kinematic measurements, is that we also can equip it with aerosols, sensors, cloud droplet, particulate sensor. It can also measure turbulence, and I'm giving a shout out to I'm not going to even be able to pronounce what AFN stands for, but I'm going to just say, go to the IRIS website and look up the Venusian project, and they're doing some cool work in terms of looking at trying to measure aerosols on Venus. So that's something neat. And then CopterSonde can go up to about 3 kilometers and does some profiling. And then the helix is something that we can equip with a multispectral camera and as well as pyrometers for looking at radiance. So to try to look at a little bit more detailed, I'm just going to kind of highlight this over is that, so we have a custom a fine array that allows us to look at turbulence, high frequency on both the Raven and the Super Raven. For looking at radiation, we can also look at radiation and surface energy with different sensors, pyrometers, and the infrared thermometers that are on the helix. And in terms of, we can also do kind of customize and look at some of the aerosols and atmospheric composition. So looking at not only just distribution, but also concentration. And also with the multispectral camera, and I'll discuss this actually even later in the talk, is looking at a surface albedo, vegetation health, and land cover as well. So here is 2 diagrams looking at and some of the different sensors related here, identifying that we have a Black Swift multi-hole probe is kind of what we started out with, so this 5-hole probe, but we have since evolved into getting and developed a 9-hole probe. And this is to allow to do the 3D wind measurements. And we also have, so the fine array is for doing turbulence flux measurements. And on the bottom is the Super Raven, and kind of identifies on certain areas where we have like the cloud droplet particulate. But here on the right is just a figure from tracers, so looking at aerosol concentration and impacts potentially on convective initiation. And so this is just showing you rows of temperature, mixing ratio, wind speed, direction, and concentration, and looking at kind of the temporal evolution and the following and before a sea breeze front and precipitation event. And so looking at the multi-rotor platforms, we have the Helix, and this is from Mosaic, and this is looking at these 2 plots are looking at surface albedo. And so looking at the albedo as a function as height, as well as changes over different land cover properties like pine, aspen, and snow. And then on, we have the CopterSonde, so that will do vertical profiles, getting pressure, temperature, relative humidity, and 2D mins. And this is showing you the graphic on the right is from Mitten CI. So that was a field campaign in 2024 that was looking at convection initiation over Lake Michigan. And so this is showing you plots of temporal evolution or of wind speed, mixing ratio, as well as theta. And we also, in addition with the platforms that we also have supporting infrastructure. So we have tracker vehicles, and we have something that's called the MERC. And so the tracker vehicles, as this photo kind of indicates, is that we launched the Raven and we launched the Ravens off of the roof using a catapult launching mechanism. And so this allows for rapid launch and response, which is especially useful when we're doing and collecting data in severe storm environments. And what is kind of nice about the tracker vehicles as well too is that the ground control station is inside the vehicles. And so this allows us to do this kind of follow me approach in which the vehicles and the UAS are moving, so it really can extend the tracks and for the operations or data collection. And then something else that we have is the MERC. And so this is a mobile UAS research command. And so this really allows for command overseeing operations in the field. It could be multiple UAS operations. We also have about a 50-foot mast that has a weather station on it, which can be used to help with calibrating sensors in the field. But what I really like here too is that we're working on the edge computing capabilities. The idea is that the edge computing capabilities would allow for us to be able to do the autonomous flight operations and really working with AI, as well as depending upon what the science objectives are and operations, is be able to do real-time computing in the field as well too. So this is something that we're actively working on. And this is just giving you a nice overview, basically saying that IRIS has been working with UAS since essentially about 2005. And as you can see, IRIS was formed in about 2015, 2016, in part from a grand challenge where we got seed money to really develop the technology and really bring the Ravens into operation. And we've been able to participate in a lot of field campaigns, and so we've, in 2024, we're able to be part of NSF-SIF. So we now have the Mobile Uncrewed Systems for Atmospheric Science. So the nice thing, too, with the SIF is that we've also been working with our partner, CEEE, which stands for Center for Engagement, Education, and Evaluation. And so partnering with them has allowed us to develop the education outreach. And so we've been able to develop something that's called a UAS micro-credential. If you go to our website, it'll take you to a link. And so this is really to help with early career scientists or potential collaborators who are interested in learning more about UAS concepts and the applications in atmospheric science. We also have working with them to develop different curriculum, whether it's for middle and high school. The idea is going out and introducing them to the platforms, virtually, but then also going out in the field and being able to collect data so that they can work with the data and really to be able to advance the learning related to atmospheric science and the UAS platforms. And so I'm going to kind of round this out a little bit here in terms of the benefits of MUSAS is that we have different platforms that can be requested, and we go out and collect data and make available to the community. We have a long record with over 1,000 flight hours, and when we go out, we're coming out with a team to collect the data, and that as a SIF can be able to be at no cost to you as well. So that was just kind of a high overview of the atmospheric sensing. I know that Adam Houston was here just a couple weeks ago, so I wasn't going to go into some of the nitty-gritty that he did in the data simulation. I'm going to be turning into a little bit and stepping into my area of expertise is looking at UAS and land surface characterizations. So I started working with these systems back in 2017. These systems are used to also do mapping, so photogrammetry, getting digital surface models. So the this is a multi-rotor, and this is Autel EVO2, so we're able to get videos. We're able to also do mapping in small areas where the fixed wing may be, have some logistical issues collecting the data. This fixed wing right here is the Trinity F90 Plus, so this is from Quantum Systems. This has a flight time of about 90 minutes, and we're able to collect thousands of images so that we can produce orthomosaics and digital surface models. And the nice thing about the fixed wing is that we use it for mapping so that we can look at vegetation health, stress, as well as surface temperature and even potentially soil moisture, as well as albedo and other things. So hopefully this works. Okay, so this is back in 2021, somewhere I think in Alabama, on one of the many damage surveys that we were doing. During times of COVID, you could see that we had to wear a mask, but you can see it has the vertical takeoff and landing capabilities, so it will ascend. And eventually, once it reaches a certain height, it's gonna then take off and transition into horizontal flight. So I'll let that finish. Okay. So with this system is that the image on the left, we see all these lines. So it essentially, the Trinity will fly in a lawnmower-like pattern. It'll collect, I think, about an image a second. So you're talking about collecting thousands, probably about 2,000 to 3,000 images over about a 60 to 90-minute flight. And we usually have to collect it with about a 75% overlap. And the reason why that we have to collect it with that overlap is that it allows, through parallax, able to do, and derive to get the products with the 3D and the 2D. So the orthomosaics are essentially, we stitch all these thousands of images together to create a geo-referenced image that we can do for analysis. And so on the right-hand side is an image from White Oak, Texas. A tornado had hit the church. You see a little bit damage to the beginning of the roof towards the near the parking lot, and then looking in the so this is a digital surface model, and it'll give us the elevation. You can see a little bit that it captures in there as well too with the elevation information. So, question for why do we care about multispectral? Well, we care about multispectral because it gives us information related to vegetation health. And so if typically looking at like near infrared and red edge, looking at multispectral bands, if it's stressed or damaged or dead, it's gonna have lower values. Whereas if it's healthy, it's gonna have higher values. So the two images on the right, you can see the one on the top right is a visible image and a corresponding multispectral image. This is showing you NDVI, normalized difference vegetation index. So the healthier vegetation is in the darker green hues, whereas the damage related to the tornado that went through here has the kind of yellowish green image colors. So I guess to say that some of this work is in collaboration with also a nonprofit that I've been working with Eric Rasmussen on this. And so the objectives of the work that I originally started at the National Weather Center and continued to work on is really, we want to be able to have more accurate and more spatial comprehensive assessment of tornadic intensity. Rural areas are of particular difficulty because unless a tornado hits a structure, it's very difficult to rate it, right? We have a lot of damage indicators for buildings, but not so much for vegetation. And so that's what this work is trying to do here. We also really want to improve our understanding of tornadic flows and their evolution. And when we're out there collecting data in the field, we're also not just doing it for science, but we're also doing it for operations. So we want to share this with National Weather Service and emergency managers. So since about 2020, I've conducted about 60 surveys across the US. Here is now the platform that I'm using. This is the Trinity Pro, so it's a slight upgrade from the F90 Plus. And then this is out in Gary, South Dakota, and they had the tall grasses, and the only thing I could take off of is this rock. And so this is our scouting drone. So we use that to be able to kind of identify where the path is and then do mapping. So now I'm going to switch, and I'm going to kind of talk about the Enderlin, North Dakota tornado. Why is this important? Because it was the first EF5 tornado since 2013. And from a science perspective, it did a significant amount of damage in rural areas. So there were 3 fatalities. A lot of the damage was into crops and trees and agricultural areas. And so we were watching this from Norman, Oklahoma, thinking, oh my goodness, this is really big. How quickly can we get up to North Dakota? So we made it up and started working. I think we got there Saturday night, and we started working the area Sunday. We also, when we're doing this, we're not just collecting UAS imagery, we're also tasking high-resolution satellite imagery to fill in the gaps. As much as we would like to be able to map the whole area with fixed wings, sometimes it's just not really possible. So the satellite is a great augment to some of the work. And so we did about 14. So they were essentially kind of 2 tornado tracks. So there's one in the cyan here, and there's another one going off. And the red the little X's are actually where we did our scouting flights. We collected, so from the scouting flights, we had over 200 images that we can use for a frame. And we have, what's really cool is that we have the data on a geoserver in AWS, so that people like NWS or even our partners that we're collaborating with can access this data. And so the yellow boxes show where we did the mapping. Of course, you know, environmental conditions like rain kind of prohibit being able to get as much data as you want. But overall, I think we did a pretty good job of a 2-person show collecting data. And so in addition, when we're out there in the field, we're not just doing the UAS mapping and scouting, but we're also walking the fields and doing ground truthing as well too. So now I'm gonna go to tree damage. And there was generally very extensive tree damage, especially to tree belts. And in particular, this 14-foot long truck, and I think it was about maybe 16 inches in diameter, was deposited about 550 feet. And you can see kind of the level of damage here. Here in the red circles, kind of showing you, this is a tree area near the Maple River. And I'm gonna kind of be focusing on that area, showing some different imagery. So before the event, it was generally kind of dense, about 40, 60-foot canopy height, and pretty much deciduous hardwood trees. Post-tornado, you can see that a vast amount of the trees were snapped. You can see some of the ground exposed, and debarking was pretty common, but I'm gonna say that with an asterisk, and you can ask me later. Looking at so based off of the tree fall, you can also get, you know, damage directions and infer and have arrows. And I know that there is a tree fall model analysis where you can take the vectors and try to estimate and back out what the near surface wind speeds were. But we're really kind of interested, not just from the near surface, we really kind of want to understand the different flows. And I think it really highlights that this is not a Rankine vortex, that this is generally a confluent flow here. What's really cool too is that we can also do a canopy height. So from a digital surface model, we can find the bare earth and then essentially create a bare earth model and then subtract the digital surface model and the digital elevation model to get the height of the features above. So this gives us an idea of also where some of the trees fell, but what's also interesting is that, you know, where some of the arrows are kind of pointing to is that the yellow values are higher heights. And so you can have a concentration or higher values here because of the trees falling together, so kind of a clump of trees. And initially we would kind of say that, the order matters in which it falls, but there's so many complicating factors here that may not necessarily be true. And that's something that's being an active area of research. So vegetation damage. Now this is kind of getting into the multispectral camera and looking at normalized difference vegetation index. Idea here is that the green hues are healthier vegetation, whereas the brown is either exposed or exposed bare soil or damaged. And so what is kind of interesting here is that we also took this and we normalized it also by the land cover type. So we normalized the NDVI values according to whether it was corn or whether it was soybean and alfalfa. What's really interesting here is that, you're seeing kind of a rapid evolution of damage, but I don't know in terms of it's over such a short distance as well in terms of tornado behavior. But what's really interesting is that you can kind of see it widen out, but I suspect in the alfalfa field is so densely planted that is not, it's not really damaged, but there probably is a little bit of damage, so we can't really necessarily say that damage is truly a function of what the tornadic wind speeds and evolution's going on. And so this is something that also what's really cool is with the canopy height model is that we can also do it with the crops too. So just like we did in tree fall, we can also do with crops. And seeing a very similar thing, I masked out the alfalfa since there was essentially no change. And this is just kind of showing you that when we go out do the ground truthing and then identifying and looking at what damage, what healthy corn looks like, and that what's really interesting is that there is some soybean scour as well. So stepping into the ground markings. People talk about cycloidal marks. Fujita had talked about suction vortices. We're not really using that suction vortices anymore, but looking at some of the marks and what might be causing those. This is showing you the white is essentially where some of material is being deposited. And then the pink is some of the driest soil, and then the green is healthier. The idea is that we can pick up on these little tiny different markings and identify the composition as well here. Another example is that, so we've heard kind of more recently that some people are talking about that cycloidal marks don't really remove vegetation. And I think that this is in a cornfield, and we're actually seeing that in these cycloidal marks, there isn't corn. And we can actually see this as well in the canopy height models. And then we also see some of the deposition streaks. And we might be thinking, well, why do we care? Is we want to really understand what are the mechanisms and dynamics in the tornado that are actually leading to these markings that we see in the field. So where am I going with this is that I'm trying to do an integrated approach. So traditionally, radar has been used and radar continues to evolve similar with satellite. Those are something we've been looking at in terms of tornado research. More recently, we've been doing high-resolution numerical models, simulations. A lot of people are doing, getting into CM1, also getting the UAS and really trying to understand and put impacts into what is going on as well. And something that also is that we're having people with forests, people who are, looking at crops and soil scientists, bringing them into the mix because it's a very important component providing context for the damage. And this is down in Copenhagen, Louisiana, and trying to understand what type of flow feature created and produced that damage where it lofted soil. And this is probably something that we've only seen twice. The other time was in the 2011 outbreak down in Philadelphia, Mississippi. So something that kind of doing in this is really also using AI, machine learning, right? And using this for classification, but also integration and helping to analyze big data sets in terms of data fusion and also really high resolution modeling. And so some of this is really looking at atmospheric science, but also geography, looking at photogrammetry, doing the multispectral analysis, and really trying to have this transdisciplinary approach to try to understand tornado dynamics and the impacts holistically. And here's an example of some of the machine learning work that we're actively working on in terms of tornado damage classification. So this is an example of interactive annotations using the human in the loop evaluation in order to extract some of the tornado damage features. So the top row, the green, is identified as healthy corn, whereas the red is damaged corn or lodged corn. The middle row is essentially mass that are identifying like debris from structures, debris from canopy, and the purple is even identifying the root ball, and that's similar to the bottom row. Something that I'd also like to give a shout out to Jeremy Sauer and Domingo Munoz Esperaz is that we're working with them to use fast eddy. The idea is that we want to be able to do high resolution simulations, and this is some preliminary work creating a tornado vortex, tornado-like vortex at a 2-meter grid spacing. And so looking at the differences in a horizontally homogeneous parameterized canopy versus a heterogeneous resolved canopy. And so with the spatial resolution, getting down and looking at fast eddy is that the idea is that we really want to get a better understanding, a better representation of what the near surface flows are. So we can really start kind of getting into understanding what radar really can't see and what is responsible for some of the damage in terms of flows. So in terms of kind of trying to bridge this whole talk together, it was really kind of centered around UAS. UAS has been very instrumental in the observing technologies and sensors with different data collection, sampling strategies, approaches. And so something that we're using UAS pre-storm, we're doing it also in storm. And so this could be with photogrammetry, having high resolution video cameras, or other sensors looking at the tornado, and then even post-event doing the surveys. And so something also, when we're just even talking about atmospheric sensing, is looking at, this all has a connection to scale. We're trying to look at different scales and try to understand the connections with microscale up to meso. And different data analysis and interpretation, AI, machine learning is going to be very important, especially when we're trying to combine these different data sets together. And so I think at the end of the day, we really want to understand the problem holistically. Here I'm talking about tornado, but we can be looking at things related to boundary layer processes or anything else. So with that, I'm gonna leave you with my contact information. You can scan the QR code, find out more about MUSAS. We also have disaster imaging, and this pilot, shout out to Bobby Geske. He took us up in a plane up in Enderlin, and we were able to get a great view. And yeah, that's it.
Thank you very much, Melissa. So a reminder online, if you have questions, Slido, and in the room, do we have questions? Ethan, catch.
Thanks. It's excellent talk. It's great to see. So I'm going to get away from tornadoes because that's not my expertise. But on the drone capability, I've seen some work in Europe in particular recently of flying swarms of drones so you can then map out in 3 dimensions the 3-dimensional wind field. Is that kind of thing something your group has thought about, or yeah, where do you sit on swarms?
Yeah, it's actually something our group has done, demonstrated in terms of at least having 2 ravens fly a distance away, trying to coordinated flight. So that's something that we're actively working on at IRIS. So that was not quite, AI or autonomous flight, but the two pilots coordinating. But that's something that we are, that's an active area of development. Yeah.
Kevin.
Thank you. This was actually very interesting. I'm curious. This is kind of a two-part question. So the drones, were they flying autonomously, or was a human in control?
So I think it depends on what the mission is. So when we're talking about the fixed wings, I think it's pretty much kind of autonomous, where you create especially for the Ravens, you set your waypoints, and then if you have like a racetrack type of you set up your mission, and then you upload it to the aircraft, and then you go ahead and execute it. So for the Ravens, yes, and even for what the Trinity, that's autonomous.
And then kind of the second part of that is, do you have a sense of if the autonomous mode or like a human pilot mode would be more capable in certain conditions versus others? Like, could you only run them with a human pilot in certain conditions, but you could run autonomously in others?
That's a kind of an interesting question, and really kind of depends on the research and objectives of the work, as well as the environmental conditions. So I think a lot of times, even if you had autonomous flight, you will always have a human overseeing the operations, right? In some capacity. It really kind of depends on the human and what the objectives are. There may be, right now, my brain's not coming up with a potential answer, but yeah.
Thank you.
Chris.
Thank you. Great talk, Melissa. I had a question on your copter sonde. You listed there an error on the 2D winds of 0.6 meters per second. And I was curious if that was primarily from GPS error or a differential in your thrust of your different motors. And then second part, how do you verify that your vertical thrust is straight up and that your four different motors aren't slightly steering you off?
Yeah, I'd honestly have to look into that and get back with you that information, because I don't know right now. But that's a great question. I say email me that.
Great.
Don't have to throw, huh? A great talk, Melissa. I do have a curiosity for one question, and the other is more on the scientific side. When you have a Super Raven, you put all the table and data and specs together. I couldn't figure out what advantages he has relative to Raven. Can you speak to that?
Of the advantages of the Super Raven?
Yeah, relative to Raven.
So the Super Raven, that is, I think with that, they had developed the different sensors, like the cloud droplet particulate sensor that was specific for the Super Raven. They also had something, I can't remember what POPs stands for, particulate. Okay.
Yeah, look at the table. They're all on the Raven side, not on the Super Raven column. But that's okay.
Okay.
Probably you're right. It's after they develop and then get more instruments and bigger payloads. Maybe that's the...
Yeah, I think the advantage of the Super Raven, if it needs to carry heavier payloads or anything, is a reason why we would be using the Super Raven in that capacity.
Okay, my next question is related to a comment you made earlier on. You may be able to get soil moisture information. So I wonder, have you any information?
I haven't had the opportunity yet to play around with the thermal band and the multispectral bands. I do believe that through some calculations that we might be able to drive it, but it's something that I will be working on. I haven't done it yet, though. Yeah.
Thank you.
I wonder if a microwave sensor of some kind might help you with that. Yeah. Brett.
Thanks. Can you say something about how much extra payload there is on the various MUSAS platforms after you've already put everything you've listed on? I mean, can somebody request them and then bring their own instrument to add?
Yes, so I believe that, so I can provide a list of the different sensors that we have, but in terms of, people can bring their own payloads, and we can see about customizing it, the Raven to be able to carry the payload. Yeah, I believe that something that they have done before. And that's kind of what we're doing with the Venusian, the AFVN, is that they have the Ravens and they have the sensor, and they're basically kind of customize the Raven to be able to be equipped with that. I think it can have maybe about a payload up to 5 pounds or so.
We have an online question from Tammy Wickworth, and she says, "Thanks, Melissa, that was a great talk. Will you please say more about your hypotheses about the crazy lofted soil samples?" Examples.
Oh my goodness. Can I throw that to Eric Rasmussen in the back of the audience? Something about maybe NWAL jet? Throw it to him, please.
Yeah, Tammy, it's really speculative, but that was a very tiny vortex core and maybe a couple of meters across, and we suspect there may have been an end wall jet, so that when the material was scoured at the surface, it was then rapidly lifted from the ground and ejected from the vortex. Most of it was thrown in this. Both of those tornadoes, the rocks in the soil was excavated to a depth of about a foot, and most of the material was tossed off to the right of the vortex path. But we're certainly welcoming you to share some other hypotheses with us.
Oh, did you have a question as well?
I did, but okay. Hi, thank you for this talk. I have a question as it relates to data quality, so it might be several questions. So you talk about having these research-grade instrumentation, and you showed, I think, a table that talked about the accuracies. Have you done any cross-validation to ensure that the measurements are within the accuracies?
I guess I would have to say that that's something that we're actively kind of working on in terms of with intercomparisons of other sensors here, right? We're trying to, with the data quality, also kind of quantify the uncertainty as well, too.
The other question that I ask is how sensitive are the measurements when you put them in different parts of the plane? I'm particularly interested in how, like, when you're doing the turbulence flux measurements, how the placement and where you place the instrument will affect the quality of the measurements, or if you've done any kind of testing of that, where you put several on an instrument in different locations and see what you're measuring.
Yeah, I mean, that's a great question. I think that's something that our engineers have played around a little bit with CFD, and we've got a wind tunnel that they have put, instrument on in terms of adjusting the placement, on the aircraft. That's something that I would have to ask them. I don't know if they've done that testing. It's a great question, though.
Thank you.
Another online question from Celine here. Thank you for the nice presentation. I am excited about the crop damage obs. Is it possible to derive a relationship or some other sort of connection between crop damage and hazard metrics, e.g. wind speeds, so that we could apply it to model data and estimate crop damage for other regions?
Yes, that's a good reason why we want to use high-resolution numerical simulations like FastEddy, right? And to be able to parameterize the different land surface features to kind of represent the different vegetation is a way at kind of getting at that question, or to be able that we might be able to answer some of that and trying to investigate some of that. And I think also part two, and I can't really read all that great right now, but for other regions, that's where working with some of the soil scientists and the crop experts would be able to maybe how that could potentially vary across region. I think right now we just have to start with some of the basics of like corn, soybean, and whatever, even just trees. Doing the modeling trees it is still something that we're working on. Or I should say maybe Jeremy and others are working on.
Thank you for the talk. Just one point regarding vegetation mapping. I would assume that vegetation, which is if there's shadow over a vegetation area, it would give us a different result when you map that against the vegetation which is not over a shadow. If there is no shadow over a vegetation area, have you encountered that kind of a problem in?
So our biggest problem is clouds,
Yeah.
right, and cloud shadow, and trying to work with that. And so, there's never any type of perfect data collection, and we do what we can to try. I think that there are some areas that have shadows and that some have no shadows. Ideally, we try to collect data, cloud-free conditions or complete clouds, right, to try to keep the illumination conditions constant. So it's something that I know that people in the remote sensing world will go out and they'll try to do multiple data collections and see if they can kind of average that out. It's a whole reason why I actually got into UAS is because I was trying to work with satellite imagery and the clouds contaminated and the data collection times. So it's a work in progress is what I'm going to say. Okay. Yes, that we take that into account and do our best to kind of calibrate it.
Thank you. Thank you.
Any further questions? If not, I want to thank you very much again, and let's give her another round of applause.